Thanks for the presentation. I'm Carmine Puglignano, a research fellow at Imperial College. The work I'm presenting today deals with the double pleating of elastic press-stressed tapes. Just a brief introduction about the reason why we are focusing on this topic. Firstly, we have natural examples showing outstanding properties in terms of adhesions, and GICO is probably the most famous case. These outstanding properties are due to the biological structure of the GICO's fingers, and our purpose will be to reproduce this behavior, this natural behavior, introducing novel bio-inspired adhesives. This is possible only if we shed light on the natural and on the physical mechanism governing adhesion and detachment. So, a brief outline of my presentation. I will introduce the model of the problem, then the mathematical formulation, and so I will be able to show you the results in terms of area displacement and press stress and press strain influence. Then I will discuss the stability of the equilibrium, and I will conclude with some final remarks. Now, this work in literature, a lot of works in literature suggest that, particularly this one was suggested by some biologists and bioengineers, suggest that the GICO behavior can be modeled simply by a double peel. And indeed, we choose to model a double peel and to try to model this mechanism. Indeed, because of symmetry reason, we can focus just on an half of the system, and in detail we can have two different configurations. The first one is this one, the configuration A, where a portion of the tape or length H is not attached to the substrate, but it is just rotated before loading, and then the load is applied to detach the tape. The alternative configuration is this other one, where the tape is completely attached to the substrate, and just before loading it is stretched. In the first case, the portion H is assumed to be positive. In the second case, it is considered negative. We will see what is the physical meaning of this difference. In both cases, we can press stress the tape, and we will see what is the difference. So, the problem can be modeled by employing the classical relation on fracture mechanics, and in particular, we haven't solved the problem with it. Lastly, we can employ the classical relations of fracture mechanics and solve the Griffith criterion that basically requires that the total energy is stationary, and basically we equal the work of adhesion to the energy release rate at the crack tip. And then we can write, it is quite straightforward to write the energy release rate as a function of the derivative of the potential energy associated to the external load and to the elastic energy, as is the size of the detached area. For the configuration we have shown, for the geometrical configuration we have shown, we can write the elastic energy and the potential energy. And and then we can solve the problem. We introduce these dimensionless quantities, and we solve the problem by introducing this set of equations. The first one probably is the most important because basically we explicitate the energy rate and we make it equal to the work of an agent. In this way we can calculate the detachment area and the displacement. And to do this we employ this geometrical condition relating the detachment area, the quantity, the length, h, and the portion of the tape that is deformed. We understand that, so the sign of h is quite important. But let's see some results. You observe in this case that this is the peeling angle in equilibrium condition as a function of the load. We observe on the left the solution with the line that correspond to negative values of h, and on the right we have the continuous line that is referred to values with the positive h. The red line is equal to h equal to 0. And now the crucial question: what is the physical difference between these two regimes? To understand and to try to reply to this question, we carry out a stability analysis of the problem, and basically we look at the energy, and we observe that on the left we have a maximum for the total energy, and so we can say that that one is an unstable equilibrium condition. On the right we have a minimum for the energy, and so we have a stable conditions. It is interesting to observe that the two states are completely separated by an energy barrier that can be overcome. So it is clear that the equilibrium state that we are able to reach strictly depends on the initial conditions. So those conditions determine the equilibrium final state. And we would like to observe what happens if we perturbate the equilibrium condition. If we are on the left in a stable region, for example, in the case of the point A, what we observe is that if we are in the point A, the peeling angles evolves towards smaller and smaller values. What we observe is that at the end of the process, the tape should attach completely to the substrate. But this is not physically possible because we have a vertical load, and so we should have an infinite stress inside the tape. But yeah, basically this is not possible, and so the tape just fails. On the contrary, if we focus on the point B, what we observe is that the tape angle increases until we reach the red line, and so we have the complete detachment. If we are in the right region, basically we evolve towards stable equilibrium. Now, just a brief look at the influence of first stress. We observe that there is no fundamental change in this difference between stability and instability, and we observe that by employing a press stress we are able to increase the limit force, but if we pass a critical value, what happens is that at very low values of the peeling angle we have to apply an external load to stabilize the system. And in any case, when the press stress passes the critical value, the peeling angle does not exceed a critical value. Now, just I can conclude looking at the displacement we observe that in this plot where we plot the displacement as a function of the filling angle, that the displacement diverges when we approach the limit angle, because basically we are touching the angle, the tape, and this can be seen also in this other slide where we plot the displacement as a function of the load. Yeah, so just to conclude, I anticipated my conclusion, but basically what we have tried to do is to introduce a model for try to understand natural filling that is a good model for understanding the natural adhesion, for example, of GECOS. We have plot filling angle as a function of the load. We have discussed the stability, and we have discussed the influence of press stress. Just a brief snapshot about the experimental validation we are trying to do. Basically, we are trying to measure the filling angle and to compare it to our theoretical predictions. So yeah, I would like to acknowledge the grant and the support part of these activities, and I would like to thank you for the attention.